So if you want to talk to him, I suggest you just send him an email and set it up yourself rather than me having to run interference for everybody. Since this is, we're not constrained that we have to all do it in one day or anything like that. So when you just write him and find the convenient time, I think that'll work better. So without further ado, he's going to talk today about architectures and flows of multicellular systems. Victor, take it away.
Okay, David. So thank you, and thank you everyone for joining. So I study indeed the multicellular systems, and what I'm specifically interested about and been fascinated, it's about how living systems shape themselves. So here behind, you can see the picture with an example. Actually, I wonder, do you see yourself on my screen? It's or it's only the presentation that you see? They have these multiple windows on the side.
I see you. We see you. I see you on the side, on the participants thing.
So you see the participants on the side as well. Okay.
Yeah.
So I try to move them.
You know, you can always change that. You can just show active speaker. Now I just see the active speaker, which is fine. But okay, yes, great. We see, right. I mean, this is a problem with Zoom, is you don't see what on the screen, what you're showing on the screen, which is really stupid. Somebody has to fix that. But so not me.
Okay, so let's go. So just behind, you can see the image of cells. This is a very simple system, two-dimensional organization of elongated cells, and the color code actually reveals the orientation of these cells. So you can see that cells, elongated cells, organized as a co-aligned domains. So this is just one example of self-assembly phenomena, but of course, I mean, everybody knows many of these, I mean, and we ourselves being an example of such thing. I would like to start from thanking to all the people who has been around or has been a part of the research. In blue, actually, I put all the people who were involved in part of this research. I'm not presenting all the research that I've done during the years that I've been in Curie, because actually I had a talk about 2 years ago, and I saw some stuff already in your department. So I will not talk about these things. So of course, Silber's lab, I mean, in which I did my postdoc, and the theory group in the Institute, and the other collaborators from Leiden Institute of Physics, and of course the funding. So let's start. So I would like to zoom out a bit and to say something about collective systems in general. So here you see fascinating examples of collective motion. And as you can be impressed, the motion in all these systems of multi-particle systems, it's coordinated and synchronized in some way, but none of the system has any conductor that actually guides the system from outside and tells it what to do. Maybe these police officers inside of this crowd could be considered as kind of conductors, but I don't think so. I assume that videos are terrible. I mean, so if something is not clear, please ask me once again. But you see sheep, birds, flocks of fishes. This is kind of very impressive systems to show usually. Today there is also some synthetic systems that the people try in this sense. But the idea that actually all this coordination and motion arise from local interaction between particles which able to move themselves in space. And they will call this self-propulsion ability activity. But from a physical point of view, what is interesting about these systems that they have a zoo of phenomena which are very interesting from just as a physicist. I mean, not only from a kind of aesthetic point of view, and this includes symmetry breaking, phase separation. So you can read the list yourself, and I think it's growing with time, and probably it's far from being complete here. So this is a kind of general scheme, a very cartoon-like scheme that shows the states of matter as a function of a driving force. In our case, it's activity, and the interaction between the particles. Because as we said, the interactions, this is what it's essential part of the active systems. By interaction, you can think a co-aligning interaction.
I'm sorry, it was a bit laggy. Can you repeat about the part of the driving force?
The driving force, yeah. So the driving force in our case, it's activity. And the interaction force is the interaction between the nearest neighbors, the close particles. How let's say co-aligning interaction, if you're talking about orientation, or the velocity correlation interaction, I mean, you can imagine many different interactions in this system. Of course, I mean, if the driving force it's very low, interactions are very strong, and so you will be in a static situation where nothing moves. So it's solid-like behavior. But there is and then you increase the active force. I mean, so you're going into. There is some noise in the background, so
it's not, everyone should mute.
You can go into. You can go away from uniform flows up to the chaotic flows. So now I would like to claim that this general kind of meta representation is also valid for multicellular systems. So now here you see the object actually of my research. These are cells. This is very, wow, a bit noisy on the background. So these are very different types of images. I mean, it's not very important to understand the details in each one of them, but assume that this is all of these images include all of these images is just a layer of cells, right? So you can see a solid-like behavior on the left side of the upper image, right? And the collective oscillations on the left side. So this is kind of transition between jammed or solid-like behavior and liquid-like behavior. So this is the last work that I showed you maybe 2 years ago, for those who remember. So this is shear flows of cells. So this is already flowing system, right? So I hope that you can see it. I mean, but the cells develop shear on the boundaries. And the two last ones, this is the system that I will talk about. So the first one starts very chaotic with many vortexes and then freezes, again going into kind of jump state. And the last one, it's this system, which seems to be also very chaotic in the bulk, but has some directional flows, which I will show you later. So this is a cell. So multicellular systems, of course, made from cells. And what you see here is it's a cell that adhere to the substrate. Please interrupt me if something is not clear, I mean, because I hope it's. I never know how it's through Zoom. I mean, I don't see your faces. I mean, so I hope it's okay. So the cell's able to move on the substrates. So see, you can cells that adhere on the substrate. So this is flat substrate, and the cells is plated on top of it. And these long protrusions, it's actually it's kind of a lamellopodium, or the adhesion points of the cells can interact with them with the substrate. So what allows this movement is it's this unit, contractile unit, which able of actin and myosin. So actin, it's a bundles, myosin, it's a motors that can pull the bundles versus each other. And this contractile unit able to generate mechanical force from a chemical energy, basically. So you add substance, you add food, you have substitutes to the cells, and they able to move, right? Otherwise they die. They actually always move. So in the cell, this actomyosin actually arranges a very complex network. And maybe the idea why these cells move, it's inside of this image here. So here on the right, you can see a cell labeled for cytoskeleton. This is this kind of a dark strings. And when it's plated on a deformable substrate, you can measure how the substrate is deformed, and you can see that cells really squeezes the substrate right toward the center. So this kind of force dipole that you can imagine, actually, it's not. You can go to higher orders, but this is the idea. So so cells actually move by friction. They squeeze on the center. So now let's dive to my data. I will not say much about technical parts, so mostly will present the results. So if there is any questions about experimental procedures and these things, I mean, so please ask me and interrupt. So this is our multicellular systems, which called the human bronchial epithelial cells. These cells exist in a state of a two-dimensional layer. Also in the real world, I mean, they make a single layer of cells on top of our bronchs. But here it's the geometry is flat, and the system is unbounded. So I couldn't put all the system inside, and actually the image also limited by its field of view. But imagine that there is no boundaries in this system at all. Now I hope that you can appreciate how it moves. But in general, I mean, I will describe what you should see. I mean, you should see very chaotic motion in the beginning, which as the time goes on, slows down and freezes. And the entire time of this experiment, it's 80 hours. Right, so of course, cells proliferate, so the density grows. I mean, there is many other biological phenomena that's going on. But if you just analyze the kinetic of the system, and the rotation of the system, so you can define two quantities. One is kinetic energy, and another the entropy. It's actually the rotational and the energy that's stored in the rotational modes. So this plot represents, I mean, what you should have been seen in the previous slide. So the system goes down by 3 orders of magnitude in the kinetic energy and also by the entropy, and it looks like both of these decreases, they go in the same with the same kinetics. So this allows to make a scale analysis. So if you divide the energy by the entropy, you actually get an area, right? So it's a simple scaling analysis, and what we see that for all these times, for all these 3 orders of magnitude, the system keeps more or less same scale, right? And this scale, it's usually attributed to the vortex size. And this is quite puzzling, right? I mean, there is very dramatic change in the system, but there is some preserved size that exists during all this experiment. So what we did then, I mean, we started to look specifically on how the vortices look like, on the statistics of the vortices. So for this, we analyzed the entire velocity field. And here above, you see the map of the velocity field, and the heat map, it's the vorticity. And from these maps, we segmented the vortexes, and they make the entire statistics. Maybe you can take a guess. I mean, what kind of a vortex statistic you would expect? Everybody is muted, right? Okay. 1, 2, 3. So I'm going to answer that myself. I mean, for now, but maybe it's better to unmute everyone. And but if people can mute themselves and answer the questions as well, it would be nice. So the vortex size, actually, the vortex area distributes exponentially. Because I mean, if you think about kind of chaotic motion, I mean, you usually think about turbulence, and in turbulence, you expect that the vortexes will be cascaded, right? It's a bit different in 3-dimensional case and 2-dimensional case, but the cascade exists in both cases. Just in 3 dimensions, we use that the energy comes from the large scales and goes down. But in 2 dimensions, you can the energy flow is going in the opposite direction. It goes from the energy injection scale and goes up. So here's so this is already suggested here. I mean, it's kind of peculiar behavior. I mean, so we'll discuss it later. And another thing that we recognize that the vorticity of the vortex or the angular velocity, it's actually also independent of the vortex area.
So I have a question. There's a peak in the distribute. I mean, there's a sort of a minimum, the exponential
this
rate.
one.
Yeah, right there.
Yeah.
So how is that compared to the cell size? That's still many tens of cell sizes, or?
I think it's a limit of our resolution, more or less, I would say. I mean, so we don't really address this this drop down.
Yeah. All right. So you don't know how to characterize whether that's real or not. Okay.
No. Actually, it's always exists, but it's again, if you see, I mean, the area here, it becomes very, very small. So this is actually the resolution of the velocity analysis grid. I mean, it's so the velocity analysis, it's not related directly to the cell size, but it's more or less the cell size. It's what we're analyzing is the entire velocity field. We're not tracking cells here. I mean, so this is a Eulerian velocimetry. I mean, it's also known as PIV. I mean, it's yes.
And Victor,
Yeah.
the fluctuation you see in angular velocity for large vortex areas, statistical.
Right? You just have much less vortexes there. I mean, so so the error goes up. Yeah. So it's you also see it in the distribution of the in the distribution of the vortex sizes. I mean, it's so the statistics becomes here very problematic. Actually. Yeah. So then we can. So I don't know any one of you. I mean, have any suggestions what to do in this point? I mean, I will tell you a story what we done. I mean, so it's so we went to look for the ideas. I mean, just in the building, which is very loaded with theoreticians of soft matter. A few students of the Gen, I mean, and guys like this. I mean, so naturally they quite immediately directly into to polymer physics or and to liquid crystals. I mean, so this is the natural way to go. And we found the answer, but a bit far away. Yeah, so this is actually the take-home message from this slide, right? So this exponential distribution and the vortex independent of the cell size, of the size of the vortex size. And the answer came from Leiden, from Luca Giomi, which published, currently we collaborate together, but I mean, this time we still didn't know personally. And he published just a few, it was about 2-3 years before our work. He published a theoretical paper which predicted exactly the same behavior. And what he analyzed is actually numeric simulation. In this case, it's numeric simulations of active nematic materials at high activity state. So you can have, it's called turbulence, but don't take this turbulence word too seriously. I mean, because there is actually it's kind of in debate between theoreticians, but I mean, the term is there, it's active turbulence. But what you see here, it's actually the same distribution as a function of the activity goes up. So you see the vortexes become smaller. This blue line, right? And actually the scaling law that he found that the vortex size actually defined by these two quantities. One is the elasticity, the Frank constant elasticity, which known in liquid crystals, right? And the activity. And this is what set the length. So the length actually is the balance, right, between the active and the elastic stresses in the system. And this is the other outcome. So I would just it actually says that the vorticity is this omega, right? It's independent of the vortex size, and these scales it's actually determined by the viscosity eta, right, divided by alpha. And it's actually also it allows to reveal kind of energy injection time into and to understand the energy injection time in this problem. What Luca? Yes.
Yeah. So question, I mean, in these theories, I mean, you basically assume some kind of rigid, let's say, so elongated objects, right?
These ones, yeah. So this is what Luca had in mind.
Right, but I mean, yours are very deformable, I think, right? That's
great. It's actually an excellent question.
Yeah, I mean, the cells are not like, you know, the long rods.
Exactly. So let me make 2 slides just to introduce to people who don't know what active nematic is the theoretical framework, and then we go to talk about the cells. But actually, if you have any insights, I would be really interested to discuss it later. So this is what Luca had in mind here. Yeah.
Victor, I have a question. Is the interaction due to, you assume the interaction is due to the exclusion to the steric effect, and then it's nematic, but if it's due to friction, then I would also expect it to be polar active.
So
And a nematic
So
one.
do you ask about cells or do you ask about this one?
No, but the theory that you showed, the figure that you showed, this is related to the cells or to this one?
So this is related to this
Cells.
material.
Let's start with the cells.
Yeah. So we go back to the cells, right? We still don't know what cells doing actually. I mean, if we can describe them as active nematic. I mean, so the point is, so I will come back to the cells in a second, right?
So I guess the main question is whether it is nematic or polar interaction.
Yeah. So I think I will provide some evidences that hopefully convenience you. Okay. So just about the hydrodynamic, yeah.
Victor, I'm sorry. I guess I'm one step behind. But what breaks the symmetry? Why do the right right vortices and the left vortices behave differently, both in the theory and the experiment?
In this system, here.
Well, I think you.
So here it's exactly symmetrical, right? I mean, so you have clockwise and anti-clockwise that look quite symmetrical.
Oh, that's -1. Okay, and in the
and also here, I mean, right? The 0 it's in the center, so you have actually symmetrical lines, right?
Okay, now I got it.
So there is no symmetry break, not for the rotation. Okay, so about nematic hydrodynamics, right? So so you can when you think about moving particles, right? Or you can imagine two scenarios, right? I mean, one is contractile, one is extensile. And what do I mean by that? So if you imagine kind of finite volume or finite area in 2 dimensions, so the particles exert some force, right, on the boundaries. And actually here you see exactly the opposite, right? So when it's contractile, it should be extensile, and the extensile should be contractile, right? So extensile particles actually push the boundary away, and the contractile, yeah. So this is this is just, I mean, yeah, this is just the opposite, right? So the stress that this particle exert, it's actually proportional. I mean, it goes in same direction with the director of these particles, right? And with the orientation of the particles. But since the particles are nematics, I mean, so you need to consider this head and tail symmetry. And again, I'm not talking about cells, so don't worry yet. And in this case, you're using this formalism which called Q tensor, which is the orientation. It describes the orientation, but takes into account the head-tail symmetry in the system. And alpha here, so let me use something. So alpha here, it's the activity. S, its order parameter, just says how particles are ordered inside of this finite volume, and N is the director. Right? So then the hydrodynamic equations, they're quite trivial. Up to this part, right? So in the stress, again, it's not. I'm just introducing the theory. I mean, that other did, right? I mean, so it's not me. If I'm said that I mean, so I'm not introducing anything. So what people do, they introduce active stress, right, next to the elastic stresses, which are passive stresses, right? They introduce active stress. And then another set of equations describes the Q tensor, actually, the orientation of the system, and it has two parts, right? So one, it's if you shear elongated particles, they will align with the flow, and the second part related to a free Landau-Degen energy, which accounts for a distortion, a relaxation from of the distortions, right? And it's here it's the expression of free Landau-Degen energy. And what you can see immediately here, I mean, so here now we focus on the upper equation, right? That by introducing active stresses, you directly introduce a scale, right? And the scale is the balance between the active part and the passive part, right? So the passive part, right? It's the elastic energy, right? Represented by the scale. It's a Frank constant, and the active part is represented by the alpha, right? So you expect for some scale to appear. Cells, okay. So who thinks that this thing is nematic, right? So here you see cells separate in the space. I mean, they're not doesn't look nematic to us. So this is why we never started from looking the answer in the nematic materials. If you look on the cells when they closely packed, you see that they become elongated, right? So they squeezed by other cells. So it's again a deformable material. It's not what people have in mind when they're talking about a nematic system, a pure nematic system, so liquid crystals. But still, the system is elongated. And we can analyze this elongation, but we never know, I mean, if the system is truly nematic until we analyze the defect in the systems. And what I mean by defects, topological defects. And here's the question of, is the system polar or nematic? So the polar system has the following topological defects with that has integer charge. And the charge actually defined by how much you need to change the degree when you're going around the defect core. By how many of 2 pi's you change the angle, basically, right? But in case of nematics, in case if the system is nematic, right, and there is no difference between head and tail, 2 other topological defects could appear, and this is these half integer defects, which are plus and minus half. If you find this, so your system is nematic. So above you see a system that is a bit different from what I showed you, what you see below, and this below is the system of our interest, but above it's a system of elongated cells that you also showed in the opening slide. So I think even by the eye, you already can see, I mean, that this half integer defect appears here. I mean, for example, here and here, you can see something by bare eye. If you don't see it, so I help you with the orientational analysis, and then you can see this minus half in red. And in green, it's the plus half, right? But apparently, when we analyze our system, same defects appear as well. It's much harder to resolve with the eye. The elongation axis of cells, it's much smaller, right? But still, the orientational analysis reveals the same pattern.
Victor.
And actually, it's not specific only to our cell. Yes. Mm-hmm.
I mean, when we're looking at these pictures, I mean, what are we actually looking at? I mean, what are these? What are the cells?
Yeah. Sorry, yeah. So cells, actually, it's the dark objects separated by white boundaries, which are the borders between the cells. Right. And this is what the images that you obtain with phase contrast microscopy, basically, right? So it's right. And they can have different contrast, but this is the general, yeah.
Okay, so is it obvious that these cells are elongated? I mean, especially in the lower picture. I mean,
it's not obvious actually, but we run. I tell you what we did. I mean, so in the paper we show a graph that presents the coherency or kind of anisotropy level of these cells. So it's much smaller. It's not much. I mean, it's probably half of the anisotropy that you have in the upper system. But then we compared it with just randomly distributed circles and rods, and it sits somewhere in between. I mean, so there is still an elongation axis that you can define, and this is what I tried to show you in this one, right? So here I think.
Did you try to visualize the actin distribution within the cells?
So in these specific experiments, no. In the elongated cells, this is what you show in the first slide, but there is no results that I have to share with you. I mean, referring this thing, but it's a bit tricky question because it's actually cells also are not exactly 2-dimensional objects, right? I mean, so there is different actin distribution on the substrates. There is some polarity in that. I mean, the fibers organized in the directed way. But it's not very easy task actually. I would say that to connect this phenomena directly to the actin distribution in the cells. It's and also keep large scale analysis of the system. I mean, so this is actually one of the tasks that I suggest to face using other methods, which kind of multi-dimensional microscopy in this case. But it's but not here.
Okay.
Okay. So this nematic organization, actually here you can see a list of cells in which we find this kind of organization with different type of anisotropy levels, and so so it's
the defect density is much higher in the bottom figure. Is there some obvious reason for that, or is it just because the anisotropy is
Yeah, so actually when you're trying to analyze the orientation, right, it's need to be suited actually to the cell, to the objects that you analyze here in this case, right? So because you're going to this kind of a sliding window over the image and trying to understand what is the structural tensor in this case. Yeah, so a smaller cells, smaller grid size. Yeah, so based on this, I would like to claim that cells actually organize as nematic liquid crystals. Okay. So what is next? I mean, so another thing that you saw that when I show you the equations, hopefully not too fast, but you remember that there's two hydrodynamic equations. One is for the orientation, and another one is for velocity. And there is and they couple to each other, right? So we should see some correlation, right, between structure and the velocity, actually. So what we did next was collecting all the defects that we recognize in the system, co-align them together, right, and overlap them on the same as a kind of average image, right? So here you see a result of this analysis. This is really an ensemble average of around 10,000 defects, right? And so this is how they look like. So what about velocity? So we did the same thing with the velocity around these defects. And this is how the velocity look like. So the velocity map reveals actually two counter-rotating vortexes, right, in case of plus half defect, which is here, right? So one rotates anti-clockwise and clockwise. And 6 rotating vortexes, harder to see. But this is kind of threefold symmetry. So if you look on the red points, you can see 3, 1, 2, 3, right? And the three blue ones. So this is quite interesting, right? Already. And apparently Luca did the same analysis for isolated vortex in the numeric simulations, right? Here, remember that we're talking about very dense vortex system, right? And it's not a system of defects with many defects very close to each other. So when Luca ran analysis of flow fields around isolated defects using hydrodynamic equations, so this is the picture that he gets. And I think it was quite striking to us, at least, the resemblance between these two. I mean, this kind of perfect simulations of isolated defect and what you get for the ensemble average in the experiment. But it's not only the resemblance. I mean, so you can learn something else from this kind of analysis. Remember that I said that, okay, so here it's right, here it's correct. You have extensile and contractile system, right? Scenarios that could take place, right? I would like you to take a guess now. I mean, so since you're active in the presentation, which is very nice, take a guess which kind of system we observe here, right? So the defect actually, it's the defect. Look on the plus half defect, right? I mean, so it's plus half defect, it's kind of bend, right? That you see here. The core of the defect is in the center. So at the core of the defect, right, the flow goes heading the direction of the bend, right? So it's actually indicated here by this arrow, right? So who votes for the extensile and who votes for the contractile? The colors has nothing to do with the American election, so it's don't worry. I mean, it's not. Okay, so if the bend trying to expand, right, and this is what you see here. So the velocity, if you have a bend, the velocity goes in the direction of the bend, right? It means that if you have any instability, it's actually increased by the velocity. This is a signature of extensile system, right? In case of a contractile system, you should have a oppositely directed vortexes, right? And which trying to retract this kind of instability back, right? So this is the summary for this slide. Everyone agrees to what I'm saying? Because it's very not trivial, because if you remember, I told you that cells actually behave as a single unit, they behave as a contractile units, right? But as a system, and this is not the only evidence, right? But it also comes from some other places. we find many systems in which cells, contractile cells, as single cells, as a collective behave as extensor particles, as extensor nematics, right? So HBAC cells, they're active, nematic, and extensile. I mean, so this is the conclusion of this one. David, how much time I left? 10 minutes? It's okay.
No, you actually have 15 more.
15. Okay. So maybe Victor, I briefly. Yeah.
Victor.
Yes.
I'm still one slide back. No, one more. So you say it is a liquid crystal when you just the slide about the static structure. So you say it's a liquid crystal, but then you have lots of defects. Probably a couple of slides back. So
yeah.
The experimental slide where you compare the cells. So yes, this one. So you say that the upper one, I understand why it is a liquid crystal with defects, but the bottom one, is it a liquid crystal or just a liquid? If you take a liquid with short range correlations in orientation, then I guess it would probably look quite the same, right?
What about topology? I mean, would you expect from many topological features in the liquid?
If you have, I don't know, I've never worked with liquids of particles which tend to align in parallel, but I would guess that it should look quite the same. So there is a short range order, and then there are changes which you may identify as.
So let me frame your question. I mean, so actually what you're asking, I mean, it's not how is you are actually asking what if the liquid crystal property comes intrinsically from the cells, or it's a hydrodynamic effect of all this squeezing of cells?
I don't think that's what I'm asking. I'm asking why do you call it a liquid crystal at all? Isn't
so
it?
If you find topological defects in the system, it's a liquid crystal. I mean, this for me it's a proof. I mean, and also for liquid crystal people. But if you're asking about the mechanism, I mean, this is the other frame that I did frame that I asked you a question. It's so this is would be legitimate. But it's here. It's I mean, for me, it's very clear evidence. I mean.
But isn't it? I mean, a liquid is just lots of defects, right? It's a liquid is a nematic with lots of defects.
Yeah, I mean, actually,
the liquid is nematic, yes.
No, a liquid. If you take a nematic phase and you hit it above the transition, then
yeah. But it still remains nematic, right? I mean, maybe here is the answer actually. Okay, so I think you're taking me to the next slide.
But Victor, actually, I have a question, I mean, which has to do with what Eli asked about. Now, let's forget for the moment about crystals and just think about it's just spheres, okay? And in 2 dimensions. Now, in principle, we expect to see some kind of exotic phases. So which means that once you get this kind of high density and ordering, then probably you get some kind of long-range orientational correlations in 2-dimensional systems. Now, I mean, I don't know whether people studied much defects in exotic phases, but I mean, I guess there should be also some kind of defects. I don't know what they should be. So maybe it is more like an exotic liquid with defects.
Actually, I would be glad to discuss it, because I think, I mean, to imagine cells as elongated particle in one, I mean, as a rods, it's definitely not the full picture.
Right. Especially,
for example, I mean,
it's especially since we actually can see them with our own eyes, and then we have to convince ourselves that what we are seeing is not correct.
Yes. Okay. So but I would say that this is the minimal description that you can give to the anisotropy of the cells. It's to imagine them as a rod. I mean, so it's I'm not saying that it's complete, but I would say that this is the minimal model that captures some at least the features that I showed. So let me proceed a bit, but because I really want to come to the second part, which is different experiment, and I will need a bit of time there. Right. So one thing that I just want to end this part with is to say that the defects, they actually remain. You remember the system slows down, right, with the time. But if you look on the correlation lengths of the director on the number of defects, which actually more or less the same should be the scales together, so you see there is no change during all these dynamic states, which is very surprising. I mean, it means that the system able to create, and so this is the typical elastic behavior that you would like to see, right? You would like you would expect that actually defects will fuse, but preferentially and no, and maybe some defects will appear, but I mean the fusion phenomena will be much stronger. Preferable, right, by the system because of the energetic considerations. But the idea here, I mean, that if the defect number remains the same, right, we can claim that that elasticity and activity, I mean, they're about the same level, and if the defect number decrease, so the system behaves, the elasticity actually takes over, right? So this is just the idea that we can also follow the formation and fusion of defects and see that there is a kind of a dynamic equilibrium of these two. And here I think I will close. There is some, maybe with this movie, I mean, just to see, I mean, how this passive-like system behaves versus not playing anymore. Okay. So let me switch to another topic, right? Which is different cellular systems, system that we analyzed. And this is kind of, my first disclosure of these results. So it's hope you will be gentle with that. And it's related to a cancer invasion model. And what, so here you see in vivo experiment where the tumor is just inserted inside of the mouse and not done by us. And they follow the tumor cells, which are these green cells, how they migrate inside of the mouse body, right? So you can get impression, actually it never plays very well. Yep. You can get impression, I mean, that first of all, that the migration takes place in confined space, right? So you can see muscle cells here, I mean, these blue ones, but in general, I mean, so there is a collective migration of cells inside of confined regions. So to address this issue, to address this kind of system, what we did, we plated cells on stripes, right? So it's same cell type, plated on stripes, and this is how it's look like. I mean, so they confined, right? Not very narrow confinements. The narrow confinements, if you remember, this is what the topic of my presentation last time. But here the confinements, they're quite large. And what we were interested in is actually the boundary effects, right? So here it's kind of zoom in on the previous movie. So here we just manually followed some cells on the boundary. So you can see that cells on the lower boundary going to the left when the cells on the upper boundary going to the right, right? And in the bulk, there is no significant, I mean, there is no net flow. I mean, it's kind of more or less chaotic motion. So here it's so we made an analysis of again of structure of these cells and the velocity of the cells.
When in the pictures in the mouse itself, did you see that this two-dimensional, the bidirectional motion? It looked
yeah,
like
so it's
going in one direction.
So first, yeah. So there is two things. I mean, so here you can see bidirectional motions, and you see that most of the motion happens at the boundaries. But actually, what you don't see that it's really three-dimensional system. I mean, it's in the confinements that you see here. I mean, they also had another dimension of depth, which is not imaged presented here. I mean, it's quite hard. I mean, to run this kind of analysis or experiments in real vivo models. But this is one of the I think one of the, let's say, the most impressive examples of collective motion of cells which are not adhered to each other. But they have some net flow, net motion, right? So here it says, so from these images you can get impression. I mean, there is multiple defects in these kind of systems, and the motion looks quite chaotic. I mean, in all around, right? So again, the heat map is the vorticity map. But there is a bit of order. I mean, cells on the border, right? So this is the distribution of cells on the border. The red one, they align with the border. And it remains disordered more or less in the bulk. So when we run this analysis through a quite large statistics of different stripes of different widths with multiple repetition, what we find it's these flows that I mentioned by manually tracking right in the movie. That you have some symmetry. There is some edge flows that develop on the boundaries, right? When in the center, I mean everything remains the same. And you can see from in the inset, right, that the edge layer where this flow appears, it's well defined. I mean, it's independent of the stripe width. Okay, was wrong wrong jump. So what we then decided to see, if you remember,
it is always they always
related some.
Victor,
always same directionally. Yeah, it's chiral.
Always the same.
Yes, the chiral. This is a nice twist here actually in this thing, because in previous systems on the narrow stripes we saw kind of both types of symmetry breaking, but here the symmetry breaking is a very chiral phenotype. So what we did, we decided to look on the defects, which we, as you have seen before, associated with the flows. And this is what you see when you analyze the polarization, or actually co-alignment of defects, right? So, I mean, so in the center, defects distribute quite randomly, we specifically look on the plus half defects, right? The finger that breaks have some symmetry break in them, having directional flows. So you see that there is some high level of polarization of the defects at the boundary layer, right? For all the widths, and the orientation of these defects at the boundaries shown in this distribution, it's almost orthogonal to the boundary. I mean, so defects facing the wall. So this is the scalar plots with a slight tilt, right? In the bulk, this gray distributions. They look very symmetrical. I mean, so it's not very uniform. Okay, so velocity map, right? At the defects reveal the following picture. So in the bulk, it's far from the edges. We see this typical two vortex pattern, right, that you saw before. But when the defect close to the edge, you see that there is some skew. I mean, right, the defect tilts. So not the defect, but the flow tilts, right? The flow tilts. I would call it anti-clockwise, right? I mean, so it's in the anti-clockwise direction, which makes actually the upper defect, right, which is the clockwise defect, the blue one, to be a bit closer to the wall, right? So the random case is just a kind of a insanity check that these patterns are not just a result of our imagination and the kind of smoothing algorithms. So we just took random points and we analyzed defects there. Okay, so what you're doing after you finding such nice phenomena, right? So you're going to ask theoreticians, what do they think about this? And again, Luca was very helpful. I mean, and now I have a gang of theoreticians that I'm very enjoying to work with. So one of them, Carlos, Luca, and Dan. So Carlos doing most pen and paper, Luca doing both, and pen and paper, and also runs simulations, and Dan doing the same as the Luca, as his postdoc. So what they actually suggested, let's introduce chiral stress in active nematic equations in the following way. So you remember that we have the active stress that we introduced was alpha Q, right? So Q is this nematic tensor. So now we introduce another part, which suggests that this, which actually determined by this tau, and this makes the system introduces chiral stresses. And this is kind of minimal substitution that you can do in order to get chirality in the system, right? So you add a bit of chiral stresses to your nematic particles. And this is the simulation result. So the bulk is an analytical result of just isolated defect, and the edge, it's indeed the simulation. And you obtain a very similar pattern, of course, much smoother than a narrow case, but still very surprisingly similar. So actually the paper that we upload this weekend, it's gonna have much more details of a comparison between simulations, because we actually investigate different features of the system, and we're able to change, not we, but actually Dan mostly, able to, in the simulations, he able to change and play with these parameters to explore the entire dependence of the system on of the chirality. And this is the general representation of what we think, actually, right? So so it doesn't matter what is the size of your confinement, right? But the boundaries themselves, the result actually a very surprising thing, which is a orthogonal rotation of the defects at the boundaries, and with addition of small chiral stress, you get this tilt, and when you actually push one of the vortexes closer to the boundary, and when you do it for all your defects, right, that range next to the boundary, so you produce long range flows from in the chaotic system. So of course, I mean, biologically, it's very interesting because it's it could give a new ideas. I mean, how to think about the migration of cells in confined spaces, and the tumor cells actually they not interact much with each other. I mean, so you need to look for some other phenomena than just kind of a sheet of cells that going from one place to another, just being adhere to each other. So here it's one of the phenomena that we can suggest and actually also show it in a not realistic but kind of toy experiment, well-controlled experiment. So I think the main active of this, it's actually also it's also important to the active matter community. I mean, it's because this kind of organization, it's never reported. I mean, it's a new phase for the active matter organization by the boundaries, and the appearance, of course, of this edge currents due to the chiral tilt. In the wider perspective, I mean, you can think that it's not very trivial. I mean, and it's not usually quite hard to convenience with these ideas, the biologist. It's the topological the topological mechanism plays a role in some biological phenomena, right? So maybe for the physicists it's not so surprising, but but I think it's the impact of direct visualization of such systems. It's of great importance. So I would like to summarize now everything, and then you take it from there, right? I mean, so it's so a bit of my perspective on what I'm doing, actually, as I think about my research. It's so let's start with the first one, right? So I write it here, right? It's actually being able to talk about living matter, right, or living system, which in this case is cells, is in the language of material science, right, and not just on expression levels and biochemical expressions as usually done in these cases. And since I mean, active material, it's real material, right? I mean, I think it's essential for this field. Another thing that I hope it's again, it's a bit kind of a physical bias point of view, right? It's to develop a kind of uniform theory that can describe variety of biological phenomena by the same physical framework. And I hope that you saw it here, but and the last thing, which is from my perspective, it's more impressive as experimentalist, is the correlation between structure and dynamics. And why it's for me it's so important. I think it's as experimentalist, many times you're trying to control your system, and I think it opens entirely new, not only to observe the phenomena, but it opens entirely new ways to control the self-shaping of active systems, which is not a trivial task at all. And of course, for biological, from biological importance of this of such control, I mean, you can imagine yourself. One last slide about kind of next future plans or future vision, right? So you saw this diagram in the beginning, and so I hope that you, I mean, from these results, you kind of get the sense that the cellular systems, they have very rich dynamic states. Even that here I mostly, I focused mainly on the chaotic behavior, chaotic phase of these cells. But there is more, I mean, actually that I'm not, in my packets, I mean, in the other modes that in the universe, on laminar flows and the transition between solid and liquid phases.